So this is the third mechanics lecture. In this lecture we're going to be looking at more than one dimension, the kinematic equations and relative velocities. So if you want to read up in the textbook about this lecture, you should read sections 2.4 and also have a look at chapter 4. So first of all, a quick recap of the most important things that we saw last lecture. In the last lecture we were looking at motion graphs. We saw that acceleration is the gradient or derivative of the velocity versus time graph, that velocity is the gradient or derivative of the displacement versus time graph, that displacement is the area under the curve or the integral of a velocity versus time graph, and that velocity is the area under the curve or integral of an acceleration versus time graph. So we also had a look at average acceleration. Average acceleration is the change in velocity over the time interval. So by change in velocity, we mean the final velocity minus the initial velocity. If we want to calculate the instantaneous acceleration, then we need to differentiate the velocity and evaluate that. We also saw that an object in free fall undergoes constant acceleration when air resistance is neglected. So now we're going to be looking at more than one dimension. So displacement, velocity, and acceleration are all vector quantities. So to answer questions when there's more than one dimension involved, then we need to split the vectors into their components and consider each of these components separately. So to practice doing this, homework set 1 for Phys 1121, questions 7 and 8, and for 1131, questions 8, 9, and 15. Okay, but what do we mean by this? How do we actually apply this? Well, to see what we mean by this, let's have a look at an example. So I'm going to paste this example on a separate page where we can work through it now. Okay, so this is quite a hard example. We've got a rabbit runs across a parking lot on which a set of coordinate axes have strangely enough been drawn. The coordinates in meters of the rabbit's position as a function of time are given by these expressions. Now, in part 1 of this question, we're asked at t equals 15 seconds, what is the rabbit's position vector r in unit vector notation and magnitude angle notation? So let's start with unit vector notation because that's easiest. So at t equals 15 seconds, then we've got x is equal to, we just need to substitute the 15 seconds into this. So this is equal to minus 0.31 times 15 squared plus 7.2 times 15 plus 28. So now we evaluate this and we get 66.25 meters. And we do the same thing for y. So this is equal to 0.22 times 15 squared minus 9.1 times 15 plus 30. And evaluating this, we end up with minus 57. So now to represent it in unit vector notation, we take x as the I direction and y as the j direction. So r is equal to, now everything here is to two significant figures, so let's write this to two significant figures. So this is 66i minus 57j, and that's meters. Now we also need to give it in magnitude angle notation. So in magnitude angle notation, we've got 66 here and then 57 downwards. And we're trying to work out what this magnitude and angle is here. So to work this out, we can use Pythagoras. These are at right angles. So this is the square root of 66 squared plus 57 squared. So when we calculate that, we get 87 to two significant figures. Now we also need to give the angle. So let's calculate this angle here. We can write, well, tan theta is equal to opposite, which is 57 over adjacent, which is this one, which is the 66. And so solving that on the calculator, we end up with theta is equal to 41 degrees, just taking the inverse tan of this. So we've got, this is 87 meters at 41 degrees below the positive x axis is one way to describe that angle. Okay, part 2 then asks us what is the velocity at t equals 15 seconds. Okay, so the velocity in the x direction is dx dt, and so we want to differentiate this. So we've got 2 times minus 0.31, so that's minus 0.62 t plus 7.2. So we'll want to work out what this is at 15 seconds. So Vx at 15 seconds, we substitute in 15. So this is minus 0.62 times 15 plus 7.2. And so this is equal to minus 2.1 meters per second. And then we'll want to do the same thing for Vy. So Vy is equal to dy dt. We get the general expression just by differentiating this. So that's 0.22 times 2 gives us 0.44 t. And then we've got minus 9.1. So Vy at 15 seconds is equal to, we'll just put 15 in for this t. So it's 0.44 times 15 minus 9.1. And solving this, we end up with minus 2.5 meters per second. So we can write V as a vector minus 2.1 I. That gives the x direction, and then we've got minus 2.5 j, and that's meters per second. And if we want it in magnitude angle, then let's sketch a little diagram. We've got 2.1 going to the left and 2.5 going down. So we want to evaluate this. Square root of 2.1 squared plus 2.5 squared. Evaluating this, and we end up with 3.3. And then we also want this angle. So we've got tan theta is equal to 2.5 over 2.1, which solving on the calculator gives us theta is equal to 50 degrees. So we can say, or 3.3 meters per second at 50 degrees below negative x-axis. Okay, and then finally, part 3, we're asked what's the acceleration. So to get the acceleration in the x direction, this is dvx dt. We'll need to differentiate this, and we get minus 0.62. And we need to evaluate that at 15 seconds. But there is no t here. So the acceleration in the x direction is always minus 0.62 meters per second. And in the y direction, we're differentiating dvy dt, and that's equal to 0.44. And again, this is constant. There's no dependence on time. So ay is equal to 0.44. So in unit vector notation, we've got a is equal to minus 0.62 I plus 0.44 j. Or we can do it in magnitude angle format. So in that case, we've got minus 0.62 going that way, and then we've got, sorry, it didn't leave much room, 0.44 going up. So we want to evaluate this one. So that's the square root of 0.62 squared plus 0.44 squared. And when we evaluate that, we get 0.76 meters per second. And then we need this angle. So we've got tan theta is equal to 0.44 over 0.62, which gives us theta is equal to 35 degrees above the negative x-axis. So in that case, you can see we solved for each of the dimensions completely independently. The x and y weren't dependent upon each other, so we just had to differentiate x twice to get the acceleration, and do the same thing to y. So the kinematic equations describe situations when the acceleration is constant in one direction, such as when an object's undergoing freefall. So let's derive these now. We're going to start from our expression a is equal to dv dt. we'll let u stand for the initial speed, the initial velocity. So this is v at t equals 0. We'll let s equal the displacement, so the final position minus the initial position. And we'll need to remember that a is constant. So these are the kinematic equations, and let's derive them now. Okay, so this is what we want to derive, and we are going to start from a is equal to dv dt. Now what we can do is write this as a dt is equal to dv, and now we're going to need to integrate to get rid of the dt and the dv. So we'll integrate both sides, and at t equals 0, the speed is u. That's how we defined u here, the initial speed. And then at time t, the speed is v. So let's do this integration. So when we integrate this side, we get at, and that's from 0 to t. And this side here is v, and that goes from u to v. So this tells us we've got at is equal to v minus u. So we can write this as v is equal to u plus at, which is this first kinematic equation here. So let's call that one a. Okay, so now what we're going to want to do is try and get an expression for the displacement s. So let's write v as ds dt. So ds dt, that's the velocity, is equal to u plus at. And now what we can do is multiply through by dt. So we've got ds is equal to u plus at times dt. And then once again, we'll integrate both sides. So we're going from time is 0 up to t, and we'll go from x initial to x final. So this is when we integrate x final minus x initial, which is how we're defining our s. So that's equal to s, and then this side we're integrating, and we get ut plus, when we integrate this, we get a half at squared, and this is at 0 and this is at t. So we've got s is equal to ut plus a half at squared. So we've now managed to get our second kinematic equation. So let's call that one b. Okay, now let's start from a to try and get this one here. So we can rewrite this one as, let's square both sides. So we've got v squared is equal to u plus at squared, which is equal to u squared plus 2uat plus a squared t squared. Now we're trying to get it to look a bit like this. So let's write this as u squared plus, I'm going to pull 2a out of each of these as a common factor. So I can times this by a half and times it by 2, and I'll pull 2a out. So we've got 2a, and then this is ut plus, when I pull 2a out of this, I've still got this half, and I've got an a here, and I've got t squared. Now why this is useful is over here in equation b, we showed that ut plus a half at squared was equal to s. So we can write this as u squared plus 2as. So we've now got our third kinematic equation here. So these are important equations that describes what happens when the acceleration remains constant. Now, one thing that we can describe using these kinematic equations is projectile motion. So projectile motion is when we throw an object like a ball, it experiences the gravitational force. So with projectile motion, we can consider the horizontal and vertical components of the motion separately. So what forces act on the projectile once it has launched? Okay, well, once an projectile's launched, the only force acting on it is the gravitational force. So this is of course assuming that air resistance is negligible, which it may or may not be, but when we're solving problems at this level, we generally assume that it's negligible. So the gravitational force is the only force which is acting on that object, and it's acting vertically downwards. So a question for us to try: two identical balls are launched from the same height, one with no horizontal velocity and one with a horizontal velocity of 1 meter per second. Which will hit the floor first? Well, in both these cases, the only force which is acting on the objects is the gravitational force. So the gravitational force is pulling both of them downwards. So even though this ball is traveling horizontally this way, it's still feeling the same downwards force. So they'll actually hit the floor at the same time. because their downwards acceleration is the same, and so their downwards motion is exactly the same. It's the horizontal motion which is different. So we're now going to consider the range of a projectile, which tells us how far a projectile will go. We're told to use the kinematic equations, so let's write them down. We've got v equals u plus at. We've got s equals ut plus a half at squared, and we've got v squared equals u squared plus 2as. Those are our three kinematic equations. And we're asked to use these to derive an expression for the maximum height. So that's the first thing that we'll want to do, the maximum height. And then we'll want to do the time of flight and finally the range of a projectile launched with an initial speed u. So let's draw a little diagram of our projectile. It's launched with a speed u at an angle theta above the horizontal. Okay, so it's launched up like that. And we can assume that the ground is a horizontal plane. So what's going to happen is it's going to follow a parabolic path like this. So this is u and this is theta. And then what it'll be useful to do is to consider u if we break it into a horizontal and a vertical component. So we can split it up like this. This is theta in here. Here's the horizontal component. So that's ux, and that's equal to u cos theta. And then here's uy, the vertical component, and that's equal to u sine theta. So we're looking to calculate the maximum height. So on our diagram, the maximum height is here. And what do we know actually happens at maximum height? Well, at maximum height, the vertical speed, Vy, must be equal to 0. Let's suppose Vy was positive but not 0. Well, in that case, it's still traveling upwards. So if it's still traveling upwards, it can't be at maximum height yet. How about if Vy was negative? Well, if it's negative, it means that it's been traveling down. So that means that we have to go back in time to when it was traveling up. So when it just switched from traveling up to traveling down is when it's at maximum height. So this is what we know happens at maximum height. Okay, so let's look at our kinematic equations and work out, well, which one's going to be most useful? Given that we know Vy and we know our initial speed, then which one's going to be most useful for calculating the height? Well, this has got things we know, but it doesn't give us the height. This one here, s, that will be the height, but we don't know t, so that's possibly not useful yet. V squared equals u squared. We know v, we know u, and this gives us the height, and we do know the acceleration as well. It's just the acceleration due to gravity. So this is the most useful equation for this case. So let's write this down for the vertical case. We've got Vy squared is equal to uy squared plus, well, let's not actually write plus yet. We've got plus 2a, but a is equal to g, and it's down, so negative. So minus 2g times s. So what we're trying to do is get this height. So at maximum height, we can substitute in Vy equals 0. So we've got 0 is equal to uy, which is u squared sine squared theta, minus 2g, and this s, that's the displacement of maximum height. So that's the maximum height here. So we can rearrange this and write, well, the maximum height is equal to u squared sine squared theta divided by 2g. So we've derived a nice expression now for that maximum height. Now next, we're asked to calculate the time of flight. Now, like we did here, we defined what happens at the maximum height. Well, the flight ends when it reaches the ground over here. So flight ends when s is equal to 0. So if we can find when s equals 0, then we've got our time of flight. So let's look at these kinematic equations again and see which one's going to be most useful for this situation. So we know s, so we'll want to use one of these ones with s. And what we're trying to do is find t. So this one's not useful this time because it doesn't tell us about t. So this one is going to be the useful one for calculating this next thing. So let's write this one down. We've got s equals ut plus a half at squared. And we want a vertical displacement of 0. So we'll be doing the vertical components. So we've got 0 is equal to the vertical initial velocity is u sine theta, and that's times t, minus a half times g t squared. And we're trying to solve this for t. So let's pull t out as a common factor. So we've got then u sine theta minus a half gt. Okay, so this tells us that t equals 0 is one solution, which is good because that's when it left the ground. It left the ground at t equals 0. So we'd want that to be one solution. But it's not the solution we're looking for. We're looking for the other solution, which occurs when this part of the expression is 0. So this will be 0 when we've got u sine theta is equal to a half gt. So that will tell us t is equal to 2u sine theta over g. So this here tells us the time of flight. So this is of course assuming that this is a horizontal plane, so it's landing at the same height it left from. Okay, so finally it asks us to calculate the range. So what we know now is how long it spends in the air. Now horizontally there are no forces acting, so horizontally the acceleration is 0. So you can see that v equals u. The velocity is not changing. So horizontally, velocity does not change. So we can use this second equation again. S is equal to ut plus a half at squared, but the acceleration horizontally is 0. So we've just got that our displacement, which is our range. This is our range. A horizontal displacement, so range is equal to ut, which is equal to u cos theta times t, and we've just calculated the time it's spent in the air here, so 2u sine theta on g. So this is equal to 2u squared cos theta sine theta over g. So that expression is absolutely fine, and we could leave it that way, but sometimes you'll see it written another way. So let me just show you how to get to how it's written the other way. To get to how it's written the other way, we'll need to use some of our trigonomic identities. So these are on your formula sheet, but we've got sine A plus sine B is equal to 2 sine A plus B on 2 times cos of A minus B on 2. Now, in the case when b equals 0, this tells us that sine A is equal to 2 sine A on 2 times cos A on 2. Now, this might look a bit familiar with this one here. If we let A on 2 equal theta, then you can see we've got 2 A on 2, A on 2. So we can use that to rewrite this as u squared times sine A, and A is equal to 2 theta, so times sine of 2 theta on g. So this is another way of writing the range equation. Now, if you want to practice answering projectile motion questions for Phys 1121 Set 1, try questions 9 and 10. For 1131, try questions 10, 11, 12, and 16. Okay, so we're now going to consider relative velocities. So we'll be considering two reference frames. And in reference frame A, Alex is at rest. Okay, so let's draw a little diagram. Here's the floor. Here's Alex. He's standing here in reference A, very stationary. So now he sees Barbara move past with a speed VBA. Okay, so here's Barbara. I'll try and draw her looking like she's moving a bit. So she's moving this way with speed VBA, directed along the x-axis. So this here is our x-axis. So we're told that the subscript here stands for the velocity of Barbara measured by Alex. Now in Alex's reference frame, he observes a particle to have a location xPa. So let's draw our particle. Here's our particle P. Now, according to Alex, this distance here is given by xPA. And we're asked, how is this related to the position of Barbara measures for P? So if Barbara is measuring where P is relative to her, she'll measure it as this distance here. So this is going to be x of P measured by Barbara and the location of Barbara measured by Alex. Okay, now where does Alex measure Barbara to be? Well, here. So this distance here is equal to x of Barbara measured by Alex. So hopefully you can see from this little diagram that this tells us that xPA is equal to xBA plus xPB. So next, we're asked to now imagine that point P starts to move along the x-axis. So this point is now moving. The speed of P measured by Alex in frame A is given by VPA. Okay, so this is VPA that's measured by Alex, not by Barbara. And we're asked, what is the speed of P as measured by Barbara in frame B, which is, we're trying to find VPB. Well, whenever we want to find speeds, we've got that the speed is equal to dx dt. We need to differentiate the position. So we have that dxPA dt is equal to dxBA dt plus dxPB dt. So just differentiating these, we get VPA is equal to VBA plus VPB. So trying to get VPB, we just rearrange it, and we've got VPB is equal to VPA minus VBA. So that was the equation that we were trying to show. Now, we're told here that when we solve problems, we usually take the ground as the stationary reference frame. Okay, so Alex is stationary on the ground. So we could replace Alex here with the ground. So we don't always show this subscript for the ground because it just comes up so much. So often we can write this as V of P relative to B. So this is V of point P relative to Barbara is given by the velocity of P. So this is assumed to be the velocity of P in the ground's reference frame and minus the velocity of B. And these are velocities, so it's a good idea to mark them as velocities with the little squiggle underneath them. So relative velocities can happen in more than one dimension. So for example, we could have people moving in different directions over a plane instead of along a straight line. So the relative velocity equation that we've derived also holds in more than one dimension. So in this case, we can solve it either adding our vectors head to tail or by breaking our vectors into components. So to practice this, try homework set 1, questions 5 and 6 for 1121, or questions 6 and 7 for 1131. Okay, so in this problem we have a plane that moves due east. So just because it says due east, that means that's relative to the ground. So let's draw the ground's reference frame here. So this is the ground, and our plane is moving east. So this here is the velocity of the plane relative to the ground. And it says, while the pilot points the plane somewhat south of east towards a steady wind that blows to the northeast. So the wind is blowing in this direction. The plane has a velocity VPW relative to the wind with an airspeed relative to the wind of 215 kilometers per hour, directed at an angle theta south of east. So let's sketch this here. So here's east, here's south, and so we're going down like this. This is an angle theta. This is 215 kilometers per hour, and this is the velocity of the plane relative to the wind. Now we're also told that the wind has a velocity VWG, so this is of the wind relative to the ground with a speed of 65 kilometers per hour, directed 20 degrees east of north. So let's draw that on this wind reference frame as well. So ground reference frame, sorry. So it's 20 degrees east of north, and it has a magnitude of 65 kilometers per hour, and this is the velocity of the wind relative to the ground. And we're asked, what is the magnitude of the velocity of the plane relative to the ground? So we want to know what's this, and we also need to work out what's this theta. So let's write down our relative velocity equation. If we want to work out the speed of the plane relative to the ground, then according to our equation, that is equal to the speed of the plane relative to the wind minus the speed of the ground relative to the wind. Now the problem is, really, when we think about it, the ground's not moving relative to the wind, it's the wind that's moving relative to the ground. But these two things are equal and opposite. So in terms of what we've got, we can write this as the velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. And now we've got a nice vector equation because we've got this vector sketched here. We've got these two vectors. So this tells us that if we add these two vectors, this is our resultant vector. So let's add those vectors. So here's the velocity of the plane relative to the wind. This is 215. And this angle here is theta. And then we're adding head to tail the velocity of the wind relative to the ground. So that goes up like this. And we know this angle here is 20 degrees. And we know that the velocity of the plane relative to the ground, which is the resultant, is easterly. So that's the resultant there. And that's the velocity of the plane relative to the ground. Now, let's start by working out theta. Because it goes easterly, we know that the northerly components of this vector and this one, which is the velocity of the wind relative to the ground, must cancel each other out. So that's this side of this triangle must be the same as this side of this triangle. So we can write this side of this triangle as the opposite, so sine of theta times 215 is equal to this side of this triangle, so it's next to this one, so this is equal to VWG, which is 65, so this is 65.0 times cos 20. So we can solve this for theta. It's the inverse sine of 65 cos 20 over 215, and when we solve that, we end up with 16.5 degrees. So now we know this is 16.5 degrees. So now we can work out what this is. Probably the easiest way to do this is just to consider this as two triangles and work out this length and this length. So we can write, well, the magnitude of VPG, which is easterly, is equal to 215 times cos of 16.5 plus 65 times sine of 20. And solving that, we end up with 228 kilometers per hour. And we know it's easterly, but we're just asked for the magnitude. Okay, so one final kind of fun problem, the monkey and the hunter. So a hunter is hunting a monkey. They know that when they shoot the monkey, the noise from the gun will scare the monkey into letting go of the branch it is grasping. Where should the hunter aim in order to hit the monkey? Okay, so above the monkey, below the monkey, or at the monkey? Well, the answer is actually at the monkey because the bullet is going to drop at the same rate the monkey drops. So if initially they're aligned, then when the monkey lets go, they're both going to fall at the same rate and the bullet will end up hitting the monkey. Okay, so a problem. A cart is propelled over an XY plane with the acceleration component. So the X component is given by 4 meters per second and the Y component is given by minus 2 meters per second. The initial velocity has components of 8 meters per second in the X direction and 12 meters per second in the y direction. And we're asked in unit vector notation, what is the velocity of the cart when it reaches the greatest y coordinate? So we need to find the velocity, but first of all, we will need to find out when does it reach greatest y coordinate. Okay, so it'll reach the greatest y coordinate when Vy equals 0, for the same reason that when we have projectile motion, the greatest height is when it's changing direction. So we need to find out when is Vy equal to 0. So we have Ay is equal to minus 2 meters per second, and we can use, well, V is equal to U plus AT, and we're considering y components here. So we can write this as, well, Vy is equal to Uy, which is the initial y velocity, so we were told that's 12, and then plus Ay, and Ay is minus 2t. So we want to know, well, when is this 0? So solving this, we can rearrange, and we've got, well, 2t is equal to 12. So that happens when t is equal to 12 divided by 2. So that happens at 6 seconds. So we now know that we want to know the velocity at 6 seconds. So we have a velocity for Vy here. We'll also need to get a velocity for Vx. So we can write, well, Vx is equal to Ux plus Ax t. So solving this one, we've got Vx is equal to Ux, which was 8. And then the acceleration in the y direction is 4t. So we can write, well, V is equal to 8 plus 4.0 t, and this is in the x direction, so I, plus 12 minus 2t, and this is in the y direction, so j. But we want to evaluate this now at 6 seconds. So this is equal to 8 plus 4 times 6, I, plus 12 minus 2 times 6, j. So solving this one on the calculator, we've got 32i. This one's 0 because of the requirement up here that at this time it was 0. So this is the answer to this problem. Okay, so in this problem, a certain aeroplane has a speed of 290 kilometers per hour and is diving at an angle 30 degrees below the horizontal. Okay, so let's sketch this diagram. Here it is diving down like this. This is 30 degrees here, and it is traveling at 290.0 kilometers per hour. The pilot releases a radar decoy. The horizontal distance between the release point and the point where the decoy strikes the ground is 700 meters. Okay, so here it is, it releases this. So the initial velocity of the decoy is the same as the velocity of the aeroplane. But if we look down at the ground here, it travels a total distance from here where it's released of 700 meters. And we're asked, A, how long is the decoy in the air? Okay, well, we know that horizontally, no acceleration, which tells us if we're using S is equal to ut plus a half at squared, then for our x components, then this thing is 0 because the acceleration is 0. So it's just traveling at a constant horizontal velocity. And we know how far it goes horizontally. It goes 700 meters. We can also work out the initial x component of the velocity. So if we break this initial velocity, because the decoy has the same initial velocity as the aeroplane, into x and y components, then our x component is 290.0 kilometers per hour times cos of 30. So let's convert 290 kilometers per hour into meters per second. So we've got 290 kilometers per hour. So that's times 1,000 meters in a kilometer to get rid of our kilometers, and then times 60 times 60 seconds in 1 hour to get rid of these hours. So we're effectively doing 290 divided by 3.6. And when we solve that, we get 80.55 meters per second. So we can put this in here, and we've got ux is equal to 80.55 times the cos of 30. And that's times t. And so this will tell us the time to get to the ground. So t is equal to 700 over 80.55 times cos 30. And solving this, we end up with 10.0 seconds. So that's part A. Now part B, it says how high was the release point. So now we're trying to get the vertical height. So we will want to use one of the kinematic equations, the vertical ones. So I think S equals ut plus a half at squared is the best one, because we know everything here, so we can calculate the height. So h will be equal to uy. So it's going downwards. So that's 80. Well, the displacement is downwards. It ends up at, if we count the initial height as 0, then it ends up as minus h. So I'm going to leave off my negative signs for going downwards. Actually, I'll put them in. It's probably less confusing. So it ends up at a height minus h below its initial point. The initial speed is 80.55 times, this is the sine of 30, times t, which we've just calculated as 10 seconds. And then it's going downwards here with an acceleration of 9.8. So half of that's 4.90. And then that's times t squared, which is 10 squared. So now you can see that all our negative signs cancel out. So they've now left for the next line. And when we solve this, we get, well, h is equal to 897 meters. Okay, so another problem. Two ships A and B leave port at the same time. Ship A travels northwest at 24 knots. Okay, so let's draw a little diagram here. Here's ship A is traveling northwest, so like this, at 24 knots. And this is ship A. And ship B travels at 28 knots in a direction 40 degrees west of south. Okay, so ship B is traveling like this. This is 28 knots. And this is 40 degrees here towards the west. So this is west, this is east, this is north, and this is south. And we're told that 1 knot is 1 nautical mile per hour. And part A, we're asked what are the magnitude and direction of velocity of ship A relative to ship B. So we want the velocity of A relative to B. Now let's answer this by breaking it into components rather than by using the magnitude vector part. Okay, so if we want to break the velocity of A into components, then in the east-west, we've got 24, this is 45 degrees, because this was exactly northwest. So this is equal to 24 cos 45. And this one here is 24 sine 45. And then we'll break this one into components as well. So again, going west, in the westerly direction, we've got 28. Now, if this is 40, this angle in here is 50. So this is cos 50. And this one here is going to be 28 sine 50. So we'll call east-west the I direction, and we'll call north-south the J direction. Okay, so writing this down, we've got the velocity of A relative to B is equal to the velocity of A minus the velocity of B. Okay, so this is equal to minus 24 cos 45 I, the negative because it's going towards the west, and then in the j direction we've got plus 24 sine 45, and that's j. And then we've got minus the velocity of b, which is equal to minus 28 cos 50, and that's I. And then we've got minus 28 sine 50, and that's j. So we'll want to put our I and our j's together. So we've got minus 24 cos 45 plus 28 cos 50. So the plus is because we had negative, negative, and that's I. And then we've got plus 24 sine 45, and then we've got negative, negative, so again plus 28 sine 50, and this is j. So solving this on the calculator, we get 1.03 I plus 38.4 j knots. Okay, now in part A, we needed to find the magnitude of this. So we've got 1.03, and then we've got 38.4. So we want to find the magnitude of this thing. So to find the magnitude of this, we add these two together using Pythagoras' theorem. So it's 1.03 squared plus 38.4 squared. And so this gives us a magnitude of 38 knots. And then we also need to find the direction. So we want to find out what this angle in here is. This angle here will then be north theta east. So if we can work out that angle is the same as this angle, just using alternate angles on parallel lines. So we can use, well, tan theta is equal to opposite over adjacent. So that's 1.03 over 38.4. And so solving that, theta is equal to 1.5 degrees. So part B, the answer is north 1.5 degrees east. Now part C says, after what time will the ships be 160 nautical miles apart? So we're told that 1 knot is equal to 1 nautical mile per hour. And we have calculated the speed here. So we can just use, well, the time is equal to the distance divided by the speed. This is just because the speed is equal to the magnitude of the velocity, which is equal to the change in x, i.e. the distance it goes, divided by the time. So this is equal to 160, because we're trying to get 160 nautical miles, and the speed that they're traveling apart at, if we keep our significant figures, so here we've just written it down to 2 significant figures, but when we actually calculated it on the calculator, it was closer to 38.4, so let's keep that. And so when we solve this, we get 4.17. This is nautical miles, and this is in nautical miles per hour, so this answer is in hours. So this is equal to 4.2 hours to 2 significant figures. Part D then says, what will be the bearing of B, the direction of B's position, relative to A at this time? Okay, so when we were calculating this first part, we were kind of assuming that B was stationary and A was moving, and this gave us the direction that A would travel in that case. Now, we're now considering, well, what happens if we are A and we're measuring B? So this is actually makes an angle of 180 degrees with this one. It's like the opposite. So the answer to this one is south 1.5 degrees west, i.e. in the absolutely opposite direction.